So we left off yesterday, and today we'll finish up the this whole introduction to forces and some calculations and friction, and then we'll start a lab, which we will finish up tomorrow. All right. So if you look at kind of the history of science, so one of the big debates has always been, what is the universe made of? Okay, is it made up of, for a while the Greeks thought there was four elements: earth, air, wind, and fire. That was promoted by Aristotle. And that, to a certain extent, made sense at the time. And the classic example of that is like, okay, let's say you wanted to make a clay pot. Okay, well, where are you going to get the clay from? Oh, it's going to come from the earth. You're going to dig up the earth and boom, here's your clay. And then you want to boil water. Okay, fine. All right. Well, we'll cut down a tree. Well, where did the tree come from? Well, it grew up out of the earth. So the tree is just a portion of the earth that grew up. Okay. And then you light the fire, and the fire burns, and you get flames and smoke, and that goes up into the air. Okay, right. Okay. And you heat up the water, and the water evaporates. Where does the water go? Oh, it goes up into the air. And then it rains. Okay, well, where does the rain come from? Well, rain falls from the sky like it did this morning. Oh, okay, right? So in that philosophy, all you were doing is just changing the forms, okay? Where does fruit grow? Where does, grass grow? Oh, all comes from the earth. Okay, the cows eat it. You eat the fruit, okay? You're just changing that cycle. So if you're in chemistry, it was a really simple time to be in chemistry because your periodic table only had four elements on it, okay? Air, earth, wind, and fire, and that was it. And you just recombined them into different ways. And that's kind of a natural, holistic kind of view, but kind of made sense. So for about 2,000 years, from about 400 BC up until about 1680, there's about a 2,000-year gap where it was kind of the dark ages of science. They really didn't think too much about science. They had a whole bunch of other things going on, like, the Black Plague and death and war and Vikings and all this other stuff going on. Dragons, I don't know. And so then about the early 1600s, it was known as the time of enlightenment. Okay? And Galileo was one of the first big hitters, and we'll talk about Galileo later. And that kind of led to a renaissance of how science was done. And it shifted from just a thought experiment into how do you quantitatively and now analyze things. You just can't say, well, I think this is a good idea. You had to have the data, you had to have the science, you had to have the math to back it up. And so that kind of shifted the whole pendulum on how science was done. So John Dalton comes along, comes with his atomic theory, says, okay, hey, atoms are indivisible, and that was the main thing, that he didn't think atoms could be divided anymore. So, this we talked about yesterday, so imagine you have this aluminum foil, you tear it, you tear it, you tear it. Eventually you get to a point where if you can't divide it anymore and have it still be aluminum, and that's what the Greeks called an atom, and atom means indivisible. Oh, that's cool. So that lasted for a long time. And then along comes J.J. Thomson. J.J. Thomson, in the early 1900s, about 100 years ago, discovers the electron. Well, and that was cool and all, but then it's like, okay, if there's electrons, just open it. Nope. Yeah, just open it. Thank you. So, if there are electrons, which are negatively charged, then you had to have protons, right? Because that's going to balance it out, because you just can't have the universe can't exist with just negatively charged particles. There also has to be positively charged particles. And then we figured out later on that there also has to be neutrons, because you have to have neutrons to have a stable nucleus. So for whatever reason, the universe, when you looked at the recipe card, how we're going to make this particular universe, luckily the recipe called for very small negatively charged particles, very big massive positively charged particles, and very massive neutral particles. Okay, without that recipe, we wouldn't be here having this discussion. And so once they figured out the electron, they said, okay, well, what's the structure of it? Okay, and the first thing they talked about was that plum pudding model, where you had positive and negative charges evenly distributed throughout the nucleus. It was cool because it explained the stability of the nucleus, because no matter what model it was, you had to be able to explain why a nucleus was stable, why this table has been a table since 1994, okay? We don't have to worry about it. This thing's a table. That's what it's going to be. So they said, okay, well, the plum pudding model, you balance repulsion and attraction, and it was stable, and it was cool, okay? So along comes Ernest Rutherford. Ernest Rutherford is a physicist. He goes, hey, let's smash stuff at it. He shot alpha particles at a sheet of gold foil, and with the alpha particles, they didn't know what they were. That's why they called them alpha particles. And it turns out they were a helium nucleus, and without the electrons on it. And that's how he knew that they were positively charged. And so what he did is that he shot these particles at this gold foil. And what happened is that almost all of them went straight through, okay, unimpeded, okay? So it would be like me taking a tennis ball and throwing it at that wall, and almost every tennis ball that I threw went completely through the wall. Only one in about 1,000,000 times would that tennis ball bounce back. And you'd sit there and go, well, that's kind of weird. You know, it looks solid, but I throw a tennis ball at it and it goes straight through. It's kind of weird. So you got to conclude that even though it looks solid, the wall was actually mostly empty space. And so that created a problem. It was like, okay, well, how do you explain this? And so because it was positively charged, and it bounced back, like 1 in 1,000,000 would bounce back, he had to conclude that whatever it was hitting was also positively charged. And so this created a problem, because now you're saying, here's this very, 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 very small, incredibly dense nucleus with these electrons going around it. Okay, well, that's problematic, but it wasn't horrible. And here's the reason why this wasn't horrible, because all of the people that were doing this research at the time were physicists. They weren't chemists, they were physicists. The chemistry department always talks about the structure of the atom, but it was actually the physics department that figured it out. And so they said, well, maybe this looks just like a solar system, because these people were physicists, they understood gravity. And at the time, we had the motions of the planets down to, no pun intended, down to a science. Like, we could tell you exactly when Venus was going to rise, when it was going to set, what was going to happen with the moon, when there was going to be ellipses. We'd even studied the motions of the moons of Jupiter, okay? And we'll talk more about that later, and how you could use the moons of Jupiter to figure out where you are on the Earth. Okay, so we had astronomy. It was an incredibly exact science at that point. And so they said, well, they'd all studied that, and they said, okay, well, just like the sun is the center of our solar system, and the planets go around it, they said, well, that's what an atom should be. And it's like, okay, well, that's cool, right? Solid. It's just a little solar system. But here's the problem, is that when electrons orbit, and we'll talk more about this later, when anything's travel in a circle, it's accelerating because it's moving in a circle, okay? And when charged particles accelerate, they emit radiation. And so what should happen is that electrons, when they're moving and they're accelerating, they should lose energy, and as they lose energy, they should all collapse into the nucleus, because they're attracted to the nucleus because they have negatively and positively charged particles. And so that created a problem. It was like, well, okay, so much for that idea. But if you look at like the classic pictures of an atom, you'll have like a nucleus, and you have like little circles like this going around. It's known as the Bohr model. And it looked cool, okay? And it was like this little nucleus in the little solar system, and it was cool, but it didn't work. So later on, this guy by the name of Erwin Schrödinger, and Schrödinger described the motions of electrons in terms of waves. And so that prevented the electrons from collapsing. because it was a wave, and the wave had to have a certain wavelength and a certain distance to reinforce that. And then we just figured out that it's all just probability anyway. When we actually talk about electrons, and this is the annoying thing about, and I teach chemistry, I teach AP chemistry, and I can never show you like a single electron. Like the whole chemistry class is built on smoke and mirrors. It is. I don't not to ruin this, but it is. It's all, I'll vouch for this. Okay, it's built on smoke and mirrors. We don't know what electrons are doing. We have a pretty good idea. Okay, but we don't know exactly where they are because they're so small. And so, like I said yesterday, I mean, even if you look at like the edge of this surface, just right here, there's 94,000 atoms stacked side by side by side to get just that thickness of that aluminum foil. Okay, it's a daunting number, which means that all of these atoms are incredibly small, but they're mostly empty space. So on a relative scale, if you imagine like if you've been to the Kansas City Chiefs football stadium or any big football stadium, if that's the size of an atom, the nucleus is like a softball on the middle of the 50-yard line. The electrons occupy all of the space that makes up everything else, but it's mostly empty space. So literally everything that you touch, everything is mostly like 99% empty space. But you go in Bergkamp, it feels solid, you know? It's like, well, how can it be empty space? It's solid, okay? The reason that it appears solid, and we can do this, okay, you would think if it's mostly empty space, you would be able to do that. But the reason we can do that is because it's the interaction of the electrons. And the electrons, as they interact, that's what creates that appearance of being solid. But if you could shrink down to an atomic size and look at the surface of things, it's actually granular. Okay, it feels smooth, but in an atomic level, it's actually granular because of the interactions of those different electron clouds. And the other odd thing is that you've never actually touched anything. So even when you do this, your fingers aren't actually touching, because what's happening is that it's like trying to bring the two balloons together yesterday. They were negatively charged. They're going to repel each other. And that's what happens there. Those electrons are repelling each other, and they push away, so you never actually, quote, touch anything. It gets weird. So I'm just telling you. So if you ever really get into studying like what happens on an atomic level, it just gets weird. Just accept that. It's a beautiful mathematical model, but it's just really weird. Okay. So once they figured out that you have a very dense nucleus, they had to come up with another force, okay? Because the protons don't want to be near each other because they have the same charge. The protons want to go flying apart. So what they did is they came up with, it's not the most clever name in the world, but it works. They came up with a new force called the strong nuclear force, okay? So what the strong nuclear force does is that it holds together the protons and neutrons that make up the nucleus. Now, obviously the strong nuclear force has to be stronger than the electrostatic force, which is trying to push things apart. Okay, so the electrostatic force is the most diverse. We're going to study friction today, okay? So friction is caused, like when you rub your hands together, that's caused by the interaction of electrons, okay? When you touch and like clap your hands, okay, the reason that you have two like opposing things going on, you have electrostatic forces that hold your skin together, okay? It isn't like you get into a bathtub or you wash your hands and your hands are soluble in water and they dissolve, which would be really awkward. It's like, what happened to your hands, man? I washed them in the water, just kind of ate them away. Oh, that sucks, okay? So you have electrostatic forces that hold your skin together, but at the same time, when you clap your hands, you don't have to worry about part of your skin from one hand sticking to the skin on the other hand, and you pull it away, and it's like, oh man, my pinky stayed over there. Oh, what do I do now? Okay, you don't have to worry about that. Even if it's just like within your own hand, right? When you one hand clapping like this, okay? When I do this, I don't have to worry about the skin on my finger sticking to the palm of my hand, okay? It's not going to happen. So the electrostatic force is the most diverse. It allows me to make coffee. It allows us to have electricity. It allows us to have light. It allows us to write. Okay, so one of the things we've done as a civilization, it's kind of cool, is figure out how to manipulate this electrostatic force. So even if you look at, like, say, for example, you have a mechanical pencil. If you think about it, it's very complex. So what we've done is that we figured out how to take and hold those particles together to make your graphite or the lead that's in your pencil. Okay, so we hold it together to make it a graphite. You can put it in your pencil, you can write with it. But then when you write with it, then it in effect tears apart and sticks to your paper. Okay, so that, if you think about it, it's complex. We hold it together long enough to make graphite, but then when you write on your paper, then it tears apart from itself and sticks to the paper. And then it's like, okay, God forbid you make a mistake. Oh, we're going to take an eraser. Then you're going to take an eraser, and then that's going to break the bonds that hold the lead or hold the graphite to the paper. So even if you look at the simple act of writing with a pencil, it's very complex. Like, we hold them together, but then it comes apart. But then we erase, and we're going to break the bonds that hold that together. Look at how you all do laundry, okay? Laundry detergent, what does it do? Oh, it breaks the stains that hold your clothes together. But they don't break the bonds that hold the clothes itself together. It's like, man, I got a new pair of blue jeans. What happened? I washed it. It's like it just all disappeared. It all disintegrated, okay? So one of the things we figured out is that how do we break those bonds? So the one thing that we don't break, and thankfully, is the strong nuclear force. Because if we ever deal with a strong nuclear force, then we're going to release all this energy that's stored within the nucleus of the atom. Now, we do that in a controlled situation, which is how nuclear power works, okay? Nuclear power works through the process of splitting large nuclei together. When you split them together, you break that strong nuclear force, energy is given off. One of the exciting things that might happen maybe in my lifetime, but certainly I hope to see it in your lifetime, is this process of fusion, where you take light nuclei like hydrogen and you fuse it together and you produce helium, and out of that process you release a tremendous amount of energy. That's the process that's happening in the sun right now, okay? And the cool part about that is that if you can do it, your only byproduct is helium. So it's like, okay, great, we get helium. We can inhale it and talk funny. That's kind of cool, right? That's your byproduct from the fusion process is helium. So the strong nuclear force, I'm going to tell you this right now. When we have the test on forces, which is still a week and a half out, I'm going to ask you, it's going to be a multiple choice question. I'm going to ask you, what is the strongest force? Okay? Don't overthink this. Do not make it complicated. It's the strong nuclear force. That's what we call it that, okay? But it's the strongest, but it acts over the shortest distance. So for that strong nuclear force to kick in, you have to get the protons and neutrons extremely close together, like 10 to the negative 10th meters, okay? It isn't like I'm going to take two protons and put them here, and all of a sudden the strong nuclear force is going to kick in and it's going to pull it together. Oh, we're going to make a nucleus, okay? Strong nuclear force can kick in, but it acts over a very, 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 very short distance, okay? All right, now, the one that I'm not going to ask you about is called the weak nuclear force. The weak nuclear force is important. Without it, we wouldn't have the fusion process that's driving the sun. Without that, we won't get energy. We won't be here having this discussion. So the weak nuclear force is important, just not something we're going to talk about. So here's the four forces. Here's what I don't expect you to know. Gravity, always attractive. It's the great sculptor of the universe. And it's not limited by distance. Electrostatic force is the most diverse, okay, but it only works with charged particles. It can be repulsive or attractive depending upon the situation. Strong nuclear force is the strongest force. That's exactly how I'm going to ask this question. It's going to be a multiple choice question. I'm going to ask you, what is the strongest force? Okay? Oh, it's the strong nuclear force. Don't overthink it, okay? Gravity is important, but gravity is actually the weakest of the four forces. Okay. So now we kind of know how this deal plays out. So now we need to shift to Newton's laws of motion. So on the back side of those lecture notes I've given you, you got Newton's laws of motion. And you can't separate one from the other one. They all kind of work together. So the first law is this law of inertia, okay? So you get inertia, and sometimes you see this first law worded different ways. Sometimes it'll say, objects in motion remain in motion, objects at rest remain at rest until an outside force acts upon them. That's kind of the most generic way that you can put it. So basically what happens with inertia is that Mother Nature, and you've heard me say this, Mother Nature is a lazy prima donna. What that means is that Mother Nature doesn't want to change things, okay? So if I take this calculator and I put it here, Mother Nature is going to go, cool, like it, rest, great, okay? And Mother Nature is not going to make that calculator move unless I exert a force on it. So if I give it a push, then it begins to move, right? So everybody gets that part, okay? Objects at rest remain at rest until an outside force acts upon it. That isn't the issue. The issue is the second part of it. The second part says that an object in motion remains in motion until an outside force acts upon it. Now, you kind of we need to go back to the Greek philosophers about 400 BC. Okay, so imagine we've gone back in time. So Aristotle believed in this concept of natural states of motion. And so if I take this cart, okay, even with the wheels on it, and if I give it a push, okay, it's going to come to a stop. And every time, if I take a golf ball and I drop it and it's going to bounce and it's going to come to a stop, every object that we can put in motion is going to come to a stop. That could be a lab. It would be a horribly boring lab, okay, and it would drive me crazy. I said, okay, kids, we're going to drop golf balls, and we're going to observe what's going to happen to the golf balls. And every time you drop that golf ball, it's going to come to a stop. And so Aristotle says, look, that's the natural state of motion. Now, if I want to keep the golf ball bouncing, just like a basketball, I've got to keep bouncing it, okay? Because if I take that basketball and I don't keep bouncing it, right, basketball is going to come to a stop. If I want to keep this cart moving, I have to keep applying a force to it, because as soon as I stop applying a force, it comes to rest. So Aristotle said, okay, look, things come to rest because that's their natural state of motion, is for objects to be at rest. And in some ways it makes sense. But Galileo, the genius of what he said, he goes, let's flip the script a little bit. So Galileo says, well, what if we took out friction? So obviously if I take this cart, right, and I push it and I have it like this, it's going to come to a stop very, very quickly because there's a lot of friction, okay? But if I put the wheel sides down and I give it a push, it goes a lot farther. So Galileo has the genius to say, whoa. This was 2,000 years later, okay? There's a 2,000-year gap between these two ideas. So Galileo says, whoa. What if we eliminate friction? If we eliminate friction, that cart won't come to a stop. That cart will keep going and going and going and going and going. So Galileo changes this idea. He says, look, the only reason things come to a stop is because of friction. If you eliminate friction, you don't have to keep applying the force. Now, it would be somewhat like you guys, teenagers, at 6 o'clock on a Saturday morning, okay? So let's say it's 6 o'clock on a Saturday morning. Your natural state of motion at 6 o'clock on a Saturday morning is to be at rest, okay? That's it. That is your natural state of motion. That's it. You are at rest at 6 o'clock on a Saturday morning. But Mom knows that Aunt Martha is coming over for breakfast at 8 o'clock, and Aunt Martha is horribly judgy, and the house needs to be clean. So your mom is going to go to you at 6 o'clock on a Saturday morning and go, hey, get up. I need your help. And you're going, oh, Mother, seriously? It's 6 o'clock on a Saturday morning. Your mom's going, Aunt Martha's coming over, okay? I don't want to be judged. Get out of bed, okay? And so she's going to have to keep applying a force to you to keep you moving, okay? Now, let's just say, hypothetically, at 6 o'clock on a Saturday morning going, oh, I'm an early riser, okay? I want to be awake. I'll help you clean. This never happens. But let's just say, right? And if that's the case and you're in motion, I'll just keep moving because I'm excited. I'm helping clean. I can't, Martha. I don't want, it's like you can keep going with that. So Newton takes Galileo's ideas and basically repackages them into his first law of motion. So the other way that you can view this is first law is in terms of vectors. If you give an object a velocity vector, which means it has magnitude and it has direction, Mother Nature is not going to change either one of those. It's not going to change the magnitude, and it's not going to change the direction unless an outside force acts upon it. So if you think about when you drive, you have three ways to alter your velocity vectors when you drive. Your gas pedal makes your velocity vectors get bigger. Your brake pedal makes your velocity vectors get smaller, and your steering wheel changes the direction of those velocity vectors, okay? So if you're making your velocity vector get bigger, smaller, or changing the direction of it, you are accelerating, which requires a force. Now, that's the first part of this, okay? Just in terms of vectors. The other thing is what we call inertia. So inertia is only dependent upon one thing, and one thing only, and that's mass. So here's a classic example. So here I've got this little plastic model of a water molecule, 2 hydrogens and an oxygen, okay? Lightweight, okay? Doesn't have very much mass. In contrast to that, here's Hank, okay? Hank has a lot of mass. So inertia is a resistance to a change in velocity. And the only thing, and listen to me, the only thing that determines the inertia of an object is how much mass it has. So Hank has a lot of stuff in it. So all of that stuff wants to remain at rest. But once I get that stuff moving, okay, then it's really hard to stop it. So I won't mind putting my hand out here and dropping this little plastic water molecule on it. Okay, it's not going to hurt, right? Because of the fact this doesn't have very much inertia, it doesn't have very much mass, it's easy to make it slow down when it hits my hand. Now, I'm not going to do that with Hank, okay? Because Hank has a tremendous amount of stuff inside of him. And all that stuff, once you get it moving, is really, really, really hard to stop. So when you talk about inertia, and this boils down to this first law, inertia is only dependent upon mass. The more mass you have, the harder it is to get it to move. But once you get it moving, the harder it is to get it to stop. So I can take this little water molecule, move it back and forth, really simple. Okay, it's not much mass, there isn't much stuff in it. Okay, Hank, that's tough to do, mainly because of the fact that there's so much stuff inside of Hank. Right? So the more stuff you have, the more inertia that you have, the harder it is to get it to move. But once you get it moving, the harder it is to get it to stop. Now, the second law is this big sign that hangs back there that says F equals ma. Okay? So then Newton comes along and says, okay, if you want something to accelerate, okay, it's cool. That's mass times acceleration. Now let's get a couple of things straight about mass. Mass is not dependent upon a gravitational field. So if I take Hank to the moon, Hank's going to have the exact same mass on the moon as Hank does here, okay? Because it's the same amount of stuff. So as long as the amount of stuff, I realize that's a horribly imprecise definition, but it works. So I'm not going to change the amount of stuff that's inside Hank if I take Hank to the moon. Still going to be the same amount of stuff. Just like this little piece of plastic here, if I take this thing to the moon, it's still not going to have as much inertia because there isn't much stuff inside of it. So if you look at F equals ma, if I want to make this little water molecule accelerate, okay, it has a very small mass, so therefore I don't need very much force to make it accelerate. Now, if I've got Hank, right, which is massive, and I want to make Hank accelerate, okay, that takes a lot more force because he has a lot more mass. So this is why you can't look at laws separately. You have to look at how they play out in conjunction. First law says, okay, hey, mass is determined by inertia. It's tough to get things to move. And that plays into the second law that says, okay, if I want something to accelerate, the more mass it has, the more force it takes to make that thing accelerate. Then you have the third law. Third law, there's various forms of that. Basically, it says that forces are coupled. In other words, forces, for every action, there is a reaction, okay? For every force, there is an equal and opposite force. Now, notice that in that definition, it says for every, okay? Just not on Tuesdays at 10 after 8 when Bergkamp's talking about Newton's laws of motion, okay? Or not on test day when Bergkamp says, oh, I hit the table, how much force does the table exert back on my hand? The same amount, okay? This is a law. This is not a suggestion. This is, oh, sometimes it happens, sometimes it doesn't, okay? It happens all the time. So here's a classic example. So what you're going to use in this lab, I'm going to use these a lot. This is called a Newton scale, oddly enough, because we generates a measurement measured in newtons and we use it to measure force. So to turn it on, oddly enough, there's an on and off button. So hold that down. And these are digital, so you don't have to worry about the rounding or anything, okay? And so depending upon how you use the scale, like in the lab, sometimes you're going to use it to pull things horizontally. Sometimes you're going to use it to lift things up. So like what I want to do is that I want to find the weight of this block. This is one of the things you're going to do in the lab. So when you do this, I'm going to use the scale like this. So right now the scale is reading 0.06 newtons. I want to re-zero it so that it's reading 0 in the direction that I'm going to use it. So I'm going to hold this up, and then down here it just says the same button that's the on-off button is the 0 button. So if you've been in chemistry and you've used our digital scales, like there's the tare button that resets it to 0, that's what this does. So just hit that 0 button, and oddly enough, the scale is now reading 0. So I'm going to take this, I'm going to lift up this block, I'm going to need this number later on, and I'm going to hold this up, and I get 3.83 newtons. So here's this block of wood. So what that tells me, and here's the earth, and this is not to scale, but you get the idea. So here's the earth. So the earth is pulling down on that block with the force of 3.83 newtons. Cool, right? I let go of it. It begins to fall rather quickly. And it begins to accelerate, right? Because we have an imbalanced force, 3.83 newtons. So, but when I drop this, everybody gets the idea that, oh, there's a force exerted being on the block because we can see the block move. Oh, we got that. Now, by Newton's third law, there is an equal and opposite force. So what that means is that the block is pulling up on the earth also with the force of 3.83 newtons. Now, the earth is massive, okay? The earth is massive. Because the earth is so big, it has a lot of inertia because it has a lot of mass. So when I drop this, the block accelerates rather quickly at 9.8 meters per second squared. The earth doesn't. Technically, we can calculate that acceleration. It's a really small number, okay? And thankfully, accelerations aren't equal and opposite. It isn't like I drop this block and the earth begins to accelerate upward at the same rate that the block accelerates downward. That would be really weird, okay? Because like playing basketball on Friday night, every time someone would like bounce a ball, if the earth accelerated in the opposite direction the same way that the basketball does, the earth would just be bouncing all over the place, right? It'd be horrible. So the forces are equal and opposite, but the accelerations aren't. So when I drop this block, there's a downward force of 3.83 newtons, but there's an upward force of 3.83 newtons that the block is exerting on the earth. Forces, always, no exceptions. Equal and opposite, balanced, there's no exception. If I push down on this table, table pushes back up on me with an equal and opposite force. One of the things you're going to do is that you're going to take a scale and you're going to pull a block, okay? So I'm going to take this, I'm going to pull this block like this, and that's about 0.8 newtons. So when I pull that block right here with that Newton scale, and I pull at 0.83 newtons, that means the block is pulling back at a negative 0.83 newtons, okay? Every force, everyone, there's no exceptions. If I push down on that table, the table pushes back on me. You jump up in the air, you exert a force on the earth. The earth exerts an equal and opposite force on you, okay? There's no exceptions to this rule whatsoever. Okay. Now we have the sets. Now we can kind of begin to lay this out into formulas and ideas and labs. So what you're going to do is that you're going to take this block and we're going to calculate some different things. So one of them is this block is going to sit here initially on this book. Okay? Now, as it sits here on this book, we took the scale and we hung it up and we did this, we zeroed it, and we hung it up like this from the scale, and we got 3.83 newtons. So at this point when it's sitting here, we're going to have some different forces. One of them is we're going to call this Fg, and I'm going to make that negative. So this Fg stands for the gravitational force between the block and the earth. Now, in this class, okay, listen to me very, very carefully. You have to get used to the terminology. In this class, when I talk about what something weighs, I'm talking about a gravitational force measured in newtons. It is not kilograms, it is not pounds, okay? It is only newtons. So in a physics setting, like we're in right now, when I talk about the weight of a block, that is a measure of the gravitational interaction between this block and the strange rock that we're on, okay? If I want mass, I will ask for kilograms, okay? If I say mass, that means you're going to go kilograms. But if I say what does it weigh, what is the gravitational force, that type of thing, that is newtons, okay? So there's only two ways you can talk about this block. You can talk about its mass in kilograms, or you can talk about its weight in newtons. Not pounds, not grams, nothing. You only have two options. Mass, kilograms, weight, newtons. That's it, nothing else. So as this sits here, there's a gravitational force of negative 3.83 newtons. Now, the table, or the book, is pushing up with an equal and opposite force of a positive 3.83 newtons. Now, this Fn stands for force normal. Okay? That's a horrible part. Okay, but you get the idea. Now, on your equation sheet, you will see that force normal equals Fg cosine theta. This is technically how you calculate force normal. Technically, you need an angle, okay? Well, on flat surfaces, which is what we're going to be dealing with until we get into inclined planes late next week, the angle is going to be 90 degrees. Excuse me, the angle is going to be 0. It's going to be flat, okay? So if you take the cosine of 0 degrees, anybody remember what the cosine of 0 is? 1. So the cosine of 0 is 1. So until we get into inclined planes, don't worry about the cosine part of this. So what this means is that on a flat surface, which is all the lab that you're going to be doing today, as soon as you know your Fg, that's the same as your normal force, okay? These are forces. These aren't masses. These aren't pounds. These are forces. So this is why that normal force is 3.83 newtons. Now, we need to talk about something very important at this point. I have two forces. I have gravity pulling down at negative 3.83 newtons, and I have my normal force at positive 3.83. Now, check my math, but if I add those together, I get 0. You can punch it into your calculator if you don't believe me, but you add those two values, you're going to get 0. So if the sum of all your forces add up to equal to 0, and it doesn't matter how many forces there are, 2, 3, 4, dozen, 1,000, doesn't make any difference. If all of your forces add up to 0, what that means is that you are going to have a constant velocity. Now, that constant velocity might be 0 meters per second. It might be 2 meters per second if I'm pushing it. You might be driving your car and you have your cruise control set at 70. Okay? It's constant velocity. So as you have a situation where you're at constant velocity, no matter what it is, all of your force is going to add up to equal to 0. Okay, that's it. Now, if I take this block and I drop it, it begins to accelerate. Because what happens, if I drop it, I lose the normal force. Okay? I no longer have that force that's acting upward. So then the only force I have left is gravity, which is going to create a value of negative 3.83 newtons. Then negative 3.83 plus 0 doesn't add up to equal to 0, and then you begin to accelerate. So if you add up the forces and they don't add up to equal to 0, that means you begin to accelerate. So literally, every problem you are going to have, every problem, can only do one of two things. Either I make all your forces add up to equal to 0, for example, in this case, your gravitational force and your normal force, those add up to equal to 0, you're at a constant velocity. Right now, you have forces acting on you. Gravity is trying to pull you all down towards the center of the earth. But the chairs are providing a normal force, which is keeping that from happening. Okay? So right now, there are forces acting on you all the time. Okay? It's cool. You're just not accelerating because they all add up to equal to 0. Now, this is what we talked about yesterday. I'm not going to go up to Hector because I like Hector. But if I went up to Hector and I pulled that chair off from underneath him, we've lost the normal force. Gravity is still acting on him. Hector is going to begin to accelerate. So every problem that you look at, literally, is only going to be one of two things. Either I'm going to make all the forces add up to equal to 0, and you're at a constant velocity, or they don't add up to equal to 0 and you accelerate. And then once you accelerate, it can only be one of two things. You're either going to speed up or you're going to slow down. That's it. That's it. Literally, every force problem can only be one of those three things. Speed up, slow down, because your forces are not balanced, or you're at a constant velocity and all the forces add up to equal to 0. Okay, stand up, take a quick stretch. We're about done. Then we can start on the lab. Okay, so that was simple. Okay, y'all are sitting there. There's only two forces, gravity and normal. Block is sitting here, gravity and normal. That's it. But what we want to talk about is the role of friction. So if I take this block, and this is what you're going to do in the lab. I'm going to take this Newton scale, and I want to re-zero it because now I'm going to be pulling this thing horizontally. So I'm going to pull this thing, and listen to two words that's going to be most important. I'm going to pull it at a constant velocity, okay? So I'm going to take this block, okay? and I'm going to pull it at a constant velocity, and that takes about 0.78 newtons of force. Okay? So when I was pulling that thing at a constant velocity, that took 0.78 newtons of force. So I'm going to draw the block going this way, and I'm going to call this force applied. And I'm going to make that a positive 0.78 newtons. I can make it negative if I wanted. It's like, man, I'm feeling a little negative today. Fine, you can make that a negative value. Okay? There you go. But I'm going to make it positive. Okay? So that applied force is what I need to keep it moving. Now, I was moving it at a constant velocity. Okay, I was moving it at a constant velocity. What that means is that there is a force acting in the opposite direction, and that's going to be my force friction, which in this case is going to be negative 0.78 newtons. So here's the story. You never directly measure the frictional force. What you measure is how much force it takes to keep something moving. Now, this is where this first law of motion kicks in. Understand that the only reason that I had to keep applying a force to keep that block moving was because there was friction. If this had been the magic frictionless block, if this was the magic frictionless block, to make it move, I could just give it a tap and then it would move in a straight line at a constant speed, and it would never slow down because it's moving and it wants to keep that velocity vector. So the only reason that I have to keep applying a force is because there's friction. And everybody has this misconception that says, oh, right, you always have to have force to keep motion. Now, you don't. If that was the magic frictionless block, I wouldn't need to keep applying the force. I could just give it a tap, boom, it would keep moving. So by virtue of the fact that I have to apply that 0.78 newtons of force, the only reason that's applied is because there's a frictional force in the opposite direction. Okay, that's it. So by measuring your applied force, you know what your force friction is. Okay? So that's how we're going to indirectly measure it. So if I wanted to figure out, okay, hey, Jack's sitting in his chair back there. I want to know how much friction there is between Jack's chair and the floor. I could go back there, I could take that Newton scale, I could hook it up, tie a rope to Jack's chair, and I could drag it. And however much force that took to drag Jack is how much frictional force there is. Now, you all have kind of these non-skid things on the bottom of the chairs, right? Okay? You really don't want that sliding around too much. Now, if I have Jack sit in this chair, okay, and this chair has rollers on it, okay, it wouldn't take near as much force to drag Jack if he's sitting in this chair because there's wheels on the bottom of it. There's still some friction, but not very much, okay? So here's the main thing I want you to get. And this is what you're going to do in this lab. When you measure how much force it takes to pull something at a constant velocity, as soon as you know the value of that force, you automatically know what the frictional force is in the opposite direction. Okay? That's it. Now, you're going to draw a lot of vector diagrams with forces. You're going to draw a lot of them. So let's make sure you understand the terminology. So in the lab, this is one of the things that you're going to do. You take a block like this. You're going to figure out how much it weighs. The easiest way to do that is to just take the scale, hang it up, boom, you get the number 3.83 newtons. Okay, boom, there you go. That's it. You don't have to do, there's no math to do. You read the scale, 3.83 newtons. Which means my normal force is going to be equal and opposite to that. I measure my applied force of 0.78 newtons. My frictional force is going to be negative 0.78 newtons. Okay. When I ask you to draw a diagram like this is what we call a free body diagram. Okay? Usually it's shortened to FBD. So when you draw a free body diagram, and you're going to draw a lot of them, okay? What you want to do is imagine that that block is like a single point. And you're going to draw all the forces acting on that block from the center, okay? So in other words, here's this block. So I've got an applied force going at 0.78 newtons. I've got a frictional force. I've got my normal force. I've got my gravitational force. Now, when you all do this, you're going to set up a scale. This is going to be drawn to a specific length. So like in this one, you might let 1 Newton equal 2 centimeters, okay? Mainly because when you draw these, you don't want to draw really tiny vectors because it's really tough to draw, and more importantly, it's tough for me to see, okay? So when you draw these vectors, the reason that I'm going to let 1 Newton equal 2 centimeters is because if I let 1 centimeter equal Newton, that 0.78 vectors would only be about this long, okay? It'd be 0.78 centimeters, okay? Really tough to see. But if I let 2 centimeters equal Newton, then I'm going to double that, and then I get like 1.86 centimeters, and that's easier to draw, and it's easier for me to see, okay? So it's going to kind of depend upon the size of the magnitude. So you're going to draw it like this, free body diagram. All the vectors are acting out from the center. You're going to draw these a lot. When I say free body diagram, think a dot, boom, here are the forces acting on it. Now, the other way that you're going to draw this is this tip-to-tail method, okay? And you all did this. This is why we learned vectors first before we did forces. So I always draw my gravitational force first. So I'm going to go, okay, here's my FG, okay? Negative 3.83 newtons. And then from there, I'm going to draw my force applied. And then I'm going to draw my normal force. And then I'm going to draw my force friction. So that's positive 3.83, 0.78, and negative 0.78. Okay? So here's the deal. If you draw those vectors tip to tail, and you end up back at the origin, that means that your system is in equilibrium. That means that you're not accelerating. It doesn't mean that you're at rest. It just means that you're not accelerating. So if you draw the vectors, no matter how many they are, and you end up back at the origin, that means the system is at equilibrium and you're not accelerating. Now, if I push this block, okay, I push it, I push it, I push it, I stop pushing. As soon as I stop pushing, which force did I lose? Is it? I stopped pushing it. Which of those 4 forces disappears as soon as I stop pushing it? Yeah, I don't have the applied force. Is there still friction? Yeah. So if there's still friction, what that means is if I drew that same thing tip to tail. Here's my FG. I have my force friction. I have my force normal. Okay? Notice I don't end up back at the origin. Now, if you remember back to how you draw vectors, you draw the resultant. Remember, that was from the origin out. So if you draw these vectors tip to tail, and you have to draw a resultant, that means that you're going to accelerate. So this is what I'm telling you. Everybody says, oh, man, forces are tough. No, forces are simple. You can only work out one of 2 ways. Either the forces end up back at the origin and you're at a constant velocity, or they don't end up back at the origin and you're going to accelerate. Every time you drive your car, you are in one of 2 states of motion. Either all of the forces acting on your car add up to equal to 0 and you're at a constant velocity, or you're accelerating. You're speeding up, you're slowing down, you're changing directions. That's it, okay? Literally, every time you drive your car, either all of the forces add up to equal to 0 or they don't. Either you're accelerating or you're not. Every time you walk down the hall, you are in one of 2 states of motion. You are either at a constant velocity, you're walking along, like this, I even do the homecoming queen wave, hi. Or you look at the clock, wow, I want to be late. And then you go, oh man, I got to run. So, boom, you speed up, you start to run. Okay, yeah, you're accelerating. Oh, I get to the door. Oh, I'm going to slow down. Okay, hey, I'm going to accelerate. Every time you walk, every time you run, every time you do anything, You only have one of two options. That's the choice that you make. Am I going to accelerate, or am I going to move at a constant velocity? Those are your only two choices. Okay, so on your equation sheet, somebody have their equation sheet, you read this. Okay, so down here, let's talk about the equations that you're going to need for today's lab. So you have this FF equals mu Fn, and then you're going to need Fg equals mg. So those are the equations that you're going to need for today's lab. So let's talk about the first one. You have two lines which indicate what? Absolute value. Okay, it's an absolute value. So this FF is what we talked about, is what we call force friction. Fn we said was force normal. Now, this kind of funky looking U is the Greek letter mu, okay? And that mu represents what we call the coefficient of friction, okay? Now, let's say, and typically what you, and there's various ways you can use this equation. What you're going to do in the lab first is that we're going to try and calculate the coefficient of friction between this block of wood and my physics book, okay? So I'm going to try and calculate mu. So typically how this is written, I'm going to get mu by itself, so mu is going to equal the absolute value of force friction over force normal. The reason that we use absolute values is because you'll see that mu has no units, okay? It's just a number. So it doesn't make any sense to make it negative. So this is why we deal in absolute values. So if I wanted to calculate the coefficient of friction between this block of wood and the book, here's what I would do. I would take my force friction, which I measured by figuring out how much force it took to pull it. So it took 0.78 newtons of force to pull it. So that means that my frictional force is going to be 0.78. So I'm going to take, somebody get out a calculator. So I'm going to take 0.78 newtons, and then I'm going to divide that by my force normal. And on a flat surface, my force normal is the same as my force weight, which is the gravity pulling it down, which we said was 3.83 newtons. Now, so somebody take 0.78 and divide that by 3.83. 0 point something. Nobody has a calculator at all? There's an con. .20. Okay? Now, here's the other, there's a couple of weird things about the coefficient of friction that's different from anything that we've experienced so far. First off, the coefficient of friction has no units because it's Newton divided by newtons. Okay? This is the only time you will have a number that has no units to it. Okay? So the coefficient of friction is just a number. So there are certain things I want you to remember about the coefficient of friction. Number one, I want you to remember that it has no units, okay, because it's newtons divided by newtons, okay, it has no units. The other thing is that it is always a positive number because of the fact that we're taking the absolute value of it, okay. So coefficient of friction is never going to be negative, it's always going to be a positive number. The third thing that you will see is that mu is almost always less than or equal to 1. If you ever get a coefficient of friction of, say, like 4 or 5, even 2, you've done something wrong, okay? Coefficients of frictions are almost always less than 1. You might get them slightly above 1 if you have like really sticky tires, okay? Or really, like, you know, syrup is involved or something. But for the most part, under normal circumstances, mu is going to be less than 1. So if you ever calculate mu, and you get a big number, yeah, something went south, okay? Typically, they're around 0.2 to about 0.7. So here's what I've got. And this is what you're going to do in the lab. You're going to take a block, you're going to pull it. You're going to see how much force it takes to pull it at a constant velocity, and then you're going to calculate the coefficient of friction. Now, what we just did, what we calculated just now, is what we call the coefficient of kinetic friction. Come on. So we're going to deal with two types of friction, kinetic and static. Kinetic comes from the Greek word kinesis, which means in motion. So we're going to study kinetic energy eventually. Kinetic energy is the energy of motion. Kinetic friction is the friction associated with something moving. Okay? If you want the coefficient of static friction, so static means from rest. So the beauty of it is that it's the exact same equation. The only difference is our technique. So static means from rest. Okay? So to get the coefficient of static friction, I'm going to do the exact same thing. I'm going to take my block, I'm going to put it on the board or your table or whatever it is. Take your Newton scale, but here's where the technique is different, because this is from rest. So what you want to do there is take the block, and what you want to do is slowly increase the amount of force that's exerted on the block until it just begins to move. Okay? So this block has mass. It has inertia. It wants to remain at rest. There's friction holding it in place. So one of the things we'll talk about is what we call we're going to talk about two different types of mafia. We're going to talk about the frictional mafia. We're going to talk about the gravity mafia. Okay? And we're going to use those to explain this concept of net forces. So basically what's happening is that the frictional mafia is there going, you're a good boy. Well, I'm going to hold you here. You're a good boy. Okay? It's like this. Okay? Right? So the frictional mafia is holding it in place. And the frictional mafia is going, you want to make my block move? You got to pay tribute. You got to pay a certain amount of force. Okay? You don't pay the force, you don't move the block. Okay? So that's the frictional mafia. Okay? So I begin to pull on this thing, and at this point I'm exerting like 0.25 newtons of force. I'm exerting 0.25 newtons of force. I'm pulling on the block. The frictional mafia is going, that's not enough. I'm not going to let Tony in the block go. I'm going to call Tony. Okay? So this is a classic example of just because you exert a force on an object doesn't mean that you're going to accelerate. I'm pulling with the force of 0.25 newtons. The block isn't moving. Okay? The block is not moving. Why isn't the block moving? What have I not overcome? What's holding it in place? Friction. The frictional mafia is going, you haven't paid us enough money. We're not going to let Tony go. Okay? You pay us more money, hey, we'll let Tony go. Okay? So what we're trying to figure out is how much money we have to pay the frictional mafia so that they let Tony begin to move. Okay? 0.25 newtons is less than what the frictional mafia is demanding. So therefore the frictional mafia is going, I'm not going to let Tony go. I like Tony. I'm going to hold on to Tony. Okay? So then you go, okay, all right, we'll pay some more. So then I'm going to increase that amount of money that I'm paying to the frictional mafia. And I pull and I pull and I pull and I pull and I pull. Oh, and it just began to move. It began to move when I exerted 1.2 newtons of force. So if I want to calculate the coefficient of static friction, so mu static is the exact same idea. It took me 1.20 newtons of force to pay off the frictional mafia. So I took 1.2 newtons, because that's how much frictional force I had to pay to the frictional mafia, 1.20 newtons. The block still weighs the exact same. It still weighs 3.83 newtons of force. Okay, it's the exact same. So mathematically, it's the same formula. So, Carson, do us a favor. Take 1.20 and divide that by 3.83. That's a horrible 8, but you get the point.
0.31.
0.31. Okay? Now, what you'll notice, and this isn't always true, but it's true most of the time, is that your coefficient of static friction is bigger than your coefficient of kinetic friction. Okay? So the gravity mafia holding it in place generally takes more money than once it's moving. And if you think about it, that makes sense because the block is at rest and the block wants to stay at rest. So you have Newton's laws of motion. Then you also have the frictional mafia going, hey, we like Tony. We're going to keep Tony here. Okay? So generally speaking, not always, okay, not always, but most of the time, your static friction is going to be bigger than your kinetic friction. Okay? Not always, but most of the time. Now, one other equation. You have Fg equals mg. Okay? One of the most important equations that you're going to have. So, there's two ways that I could calculate the weight of this block. One option, and this is what you're all going to do, is that you're just going to take a scale and you're going to hold it up, and in this situation, you're just going to read a number, 3.83 newtons. So if you have a Newton scale and you want to find the weight of a block, all you have to do is hook it up, boom, there you go, easy peasy, read the scale, it's a digital number, no calculations at all. Now, the other thing that you're going to have to do on the lab is a lot of times you're going to know the mass of the object. Okay? So, for example, one of the things you're going to do is you're going to take this block and you're going to stack weights on top of it. And then you're going to pull it and you're going to see what's going to happen. So, if here's the block, let's say that you take a mass of 0.2 kilograms and you stack that 0.2 kilogram mass up on top of this. So, if you know the mass, and you want to find out what it weighs, then just take the mass in kilograms, and it has to be in kilograms. Multiply that by 9.8 meters per second squared, which in this case would get you 1.96 newtons. So there's two ways you can determine the weight of a block. Option number one, hold it up, read the scale, boom, there you go. If you know the mass of the block, take the mass, multiply that by 9.8 meters per second squared, assuming that you're on Earth, and that's how you're going to get the weight. So if you remember back to the very first lab that you all did, which seems like an eternity ago, and you took the spring, remember, and you hung the weights from it, okay? And I said, take that mass and multiply it by 9.8 meters per second squared, and just do it, and later on you'll see why. This is why you do that, okay? This is where this formula comes from. So, again, don't flip out. If you're trying to find the weight of an object, there's two ways you can do this. Either hang it from a scale, or if you know the mass, multiply that by g. Now, there are certain things that annoy me, in case you all haven't figured this out. Do not, and it's just horribly wrong. Don't say, oh, gravity is 9.8. It's a train wreck. Okay, gravity is not 9.8. Okay, you can say gravity causes an acceleration of 9.8 meters per second squared. You can say that. Okay, you can say that the weight of an object is mass times the gravitational acceleration. But just don't say, oh, how are you going to calculate the weight of the block? I'm going to take mass times gravity. Just think about that. It doesn't make any sense. How can you take mass and multiply it by gravity? Okay? No. Okay? You can take mass and multiply it by the gravitational acceleration, but don't just say, oh, mass times gravity. No, that's horrible. Stop. Okay, let me hand out the lab and then we'll get going on that. Okay. So, here's what you're gonna do. Oh, we'll finish this up tomorrow. We're just gonna get started today. So, what I want you to do is go back. You can grab a Newton scale like this, turn it on, and the first thing you're gonna do is this wood on wood. We'll worry about the aluminum, the cotton, and the sandpaper tomorrow. We're just gonna deal with the wood on wood today. So, the first thing that you need to determine is the gravitational force and the normal force. That's simple. Take your Newton scale, re-zero it, hang it up, boom, whatever number you get, that's that column. Then, you want to do the static friction column. So what you're going to do is you're going to take your block, put it on the table. You're going to, at this point, you're going to be pulling your scale like this. Make sure that you re-zero it so that when it's horizontal, it's reading 0. You're going to take this and you're going to slowly increase the pull on it until that block just begins to move. Now, the surfaces back there aren't completely uniform, so depending upon where you're pulling on the table, you might get different values. So just kind of do that until you kind of get a consistent value. So you're at rest, give it a pull, boom, there you go. So that's what's going to go here on that static. That's just a number, okay? Now, what you want to calculate is your mu static. You don't have to show me all these calculations, but at least show me the first one. So what I would want to see, there where it says mu static, this is what I would want to see. I would want to see the force that it took to pull it divided by the weight of the block. Okay, so whatever those numbers are. Then, on the kinetic friction, with that one, you're going to pull it along at a constant velocity. You're going to see how much force it takes to pull that block at a constant velocity, record that number, and then you're going to calculate the coefficient of kinetic friction, which is just going to be this calculation right here. So what I want you to get done today, okay, is that's all. I want you to go back, figure out how this works, because we only have like 5 minutes left. Take whichever block you're going to use, and you're going to use the same block tomorrow. Okay, so keep track. You can just leave your block set aside. Just keep track of which block it is. Find the weight. Figure out how much force it takes to pull it from rest, how much force it takes to pull it at a constant velocity. Get that number, and then we're done, and then you don't have any homework tonight. So.